Welcome. Today we're going to talk about Laplace's equation. So this is a new PDE, but it's related to the heat equation. So recall the heat equation. And we're going to do it in 1D for right now. It's going to be the partial derivative of U, the temperature, with respect to time is equal to K times the second partial with respect to space. And what we're going to look for is equilibrium temperature. And we're going to consider fixed boundaries. So we're going to say that U at x equals 0 is just going to be T1, and U at x equals L is going at all times is going to be T2, right? So this is what we call a Direchlet boundary condition. We also just call that, fixed temperature. Boundary condition. Okay, so with this sort of problem where we have two constant temperatures on either side of our bar, we find the equilibrium temperature. That is, so equilibrium, that's an equilibrium. Where we have no change of temperature over time. That sort of situation leads to an equation of the form second derivative of the partial with respect, or second derivative of temperature with respect to space is equal to 0. And that leads to a solution of the form, and we've done this before, and I'll just, you can just have it as a function of x only, and it's simply T1 plus T2 minus T1 over L times x. And again, that was linear. And it was of the form from 0 to L like that. So here it's T1 and there it's T2, whatever these values are, and you have some linear, so U, the temperature over the course of, this 1D interval, which represents some steel rod maybe conducting heat, is just this linear equation. So that's nice. So now recall, we can define the heat equation in 2D. So now we're switching gears here. The heat equation is, again, the change of temperature with respect to time. We're going to have x, y, and now t, so there's 3 variables, 2 variables in space and 1 variable of time, is equal to what we call the Laplacian, which is, and times a k, sorry, there has to be some sort of a thermal conductivity constant, or a thermal diffusivity constant, and that's going to be k times, and I'll write the partials in this way, uxx, that's just a little easier to write, plus uyy. Okay, and that's the second partial with respect to x, and this is the second partial with respect to y here. Okay, so this is also the Laplacian. And of course, you can see for 2D, right here, there's your, that's the same thing as over here. But now we just have a second dimension there. And so this is on some region, we'll call it D. We can, and now it's a two-dimensional region, we'll call it D. And it's going to be in the xy plane, right? And again, we have some, and just like a Direchlet boundary condition where we have temperatures at fixed endpoints of our rod, now we have to define temperature. Has to be, there is some sort of temperature U defined on the boundary with respect to time is equal to some temperature. This has to be, this is our boundary condition. So now let's consider a special case of the rectangle. So we have our 2D heat equation. as such. And now we have the rectangle, and this will be in the xy plane, going from 0 to L and 0 to H. This is in the y axis there. And that's the x axis there. All right. And so now what we're going to do then is the boundary conditions in this case is prescribe temperature on the boundary. So in this particular case, we can say that U along this zone here, and we're going to say that's equal to x, and then y is equal to 0. Now we're going to call that f1 of x. So we'll put that down there, f1 of x. Okay, and now I can call this BC 1. And now, so that's one of the boundary conditions. Now we got 3 more. So U of x, y is equal to h. That'll be the top one here. We'll call that f of 2 of x on the top. Okay, and likewise we have 2 others on this side. We'll call that U of x equals 0, y. That's going to be called g1 of y. I'll put that over here. And then finally, U of x equals L of y is equal to g2 of y, and that'll be over here. All right, so these are the boundary conditions. Now, remember, this is looking down on our plane, but in general, the goal here is to think about. I'm gonna draw the rectangle this way. So we have these temperatures. So here is we'll say that's the x, and this is the y here. And we'll have some sort of function f1. And we're going to have some function g1. Likewise, we'll have some function g2 and some sort of function f2. Okay, and what the question then is, what is u of x, y, and t going to be in the middle? We don't know what that is. We want to make a surface in here that evolves over time. But we don't know what that is yet. We don't have methods yet to solve for that equation, to solve that, but we want to get some start on this. And the first thing we always do is we're going to look for equilibrium solutions. All right, so that means we're looking for solutions of the form that have no change in time, and that is precisely what we call, and this is what we call the Laplace equation. Laplace's equation. Okay, so let's get started. And again, these are our boundary conditions right here. And the equation that goes with it is that, or we can also write it as uxx plus uyy is equal to 0. Okay. We don't need the thermal diffusivity constant because everything's set equal to 0. All right, so we want to solve this, and we're subject to these boundary conditions. So we want to know is, after we have some set temperatures, there could be some strange functions that exist on the boundary, we want to know what the temperature is like in the middle of this conducting medium. This is now sort of what you call a metal, maybe a plate that's heat conducting. So that's the kind of model we're looking at, is a metal plate that's heat conducting, and it has temperatures prescribed on the boundaries. Okay, so you could think of a lot of applied problems involving this sort of situation. Okay, so let's talk about how to solve this equation. But before we solve, we need to just do some theory real quick. So recall from before with the heat equation, we had boundary conditions of the form either u is equal to 0 on the boundary, or the partial of u with respect to x was equal to 0 on either x equals 0 or L. So on boundary, I mean x is equal to 0 or L, right? And that was in 1D. And so these were equal to 0, and we also had some operator that we can write LU is equal to 0, right? So together with this 0 or that 0 and this linear operator set to equal to 0, we had what we call a homogeneous problem. And what we mean by homogeneous and why we call it that is if U and so if W and V are solutions, then W plus V is also a solution, right? And why is that the case? Because again, this is a linear operator, so and each one of them is 0, but also both satisfy what we call homogeneous boundary conditions. So W is 0 and V is 0 on the boundary. That means that W plus V is also 0 on the boundary. And likewise, if I'm thinking of a no-flux boundary condition, you get the same result there, right? So that works out nice. But now let's look at our new problem. We had these prescribed temperatures. Now we have a new L. So now that was with the heat equation. Now with Laplace, we have a linear operator. We set it equal to 0, so that's definitely homogeneous, at least in that respect. But our boundary conditions involve functions of x. Whether it be on either side, but at any rate, you had all those four sides, and you had temperatures that were prescribed that were potentially non-zero. That is, so U is not necessarily equal to 0 on the boundary. So what this means is that our problem, our Laplace PDE problem, is non-homogeneous. Okay, and so what do we mean by that? We mean that if W and V are solutions, well, certainly it's true that the sum will solve the PDE still. That's 0 and that's 0. But the problem is W plus V is not going to have the same boundary condition. Well, it'll actually be 2 times original boundary condition. All right, and so W plus V does not solve the PDE with boundary condition. So we don't have that nice linearity property or that superposition property. So what this means is with Direchlet boundary conditions is that superposition does not hold or does not apply. We don't have superposition of solutions. Okay, so that looks nice. So that was there's a little bit of theory involved. So now we have to, again, let's write down the problem again. We have, here's our our rectangle. Say that's the x direction. This is the y direction. So we have h, 0, 0, L. And then we have some function on this side which we'll call f1. And that function on this side we'll call f2. And this function g1, and another function here g2. All right. So although we don't have superposition in general, but we do have superposition for some special subsets. If I have u, and I'm going to call it u1, which is equal to 0 on if I have a solution, u1 is equal to 0 on I need to say this correctly. It's equal to 0 on. It's equal to 0 here, and it's equal to 0 here, and it's equal to 0 here. But on this boundary, u1 is equal to f1 of x. And then if we have u2 is equal, u2, we have another solution here. We'll call it u2, which is equal to f2 on this side, on the top side, but it's 0 everywhere else. Then and so on and so forth for u3 and u4 for g1 and g2 on that side, right? So we'll call that u4, and this is u3. But it's 0 on all the other sides. Then we know that the full solution will be a superposition. So that means u, x comma y. Remember, we're not talking about, time is, there's no t here. The reason there's no t is because we're considering the equilibrium solution where nothing changes in time. So it's only a view of x of y. Will be the sum of our 4 functions, each satisfying one of the side boundary conditions and 0 in the others. Okay. So let's go try an example here. Okay. So I'll actually. So that means what this means. Hold on, I'm going to go back here. So what this means, we can solve for u1, u2, and u3, and u4 individually. And then add them up at the end. So let's now consider solving for what I'll call it u2 of x comma y. All right, so again, this is the condition. I'll put it like that. So that's f2 of x is equal to, and I'll put it up there, is equal to u2 of x comma y equals h. And then everywhere else, u2 is equal to 0. All right, so how do we find this solution? So we're going to do an example. We're going to do the example of f2 of x is equal to sine pi x. And we're going to consider the special case of L equals h equals 1. So the unit square. All right, and so that's exactly this sort of shape. It just looks like that. All right, and it's 0 on all the other boundaries. So we're going to solve for that one today. And so how do we solve for this one? Let's go through carefully and do it. So what we're going to use is again the method is separation of variables. All right, so the separation of variables gets a little trickier with the Laplace equation relative to the heat equation. So we have to be careful, and every time we do a different side, we're going to have to make sure that we pay attention to all the steps, because each side will be a little different, but they all will go along the same basic pattern. So let's do this top side here with that boundary condition set in place, and we'll take the particular example of F2. But I'm going to do it with a general. I'm going to solve first for general H and L and F2. And then later I'll apply these particular numerical values. So let's do it. Okay, so we're going to, again, this method of separation of variables is to guess u of x. We're doing u2 here, x comma y, but I'm going to drop that 2. We don't need it. We'll just say it's u, just to keep things simple, is going to be of the form p of x, q of y. All right, so we're not doing time anymore, but we're just going to switch our variables around. So we have these two formulas, and again, the PDE, let's write it over here. The PDE is going to be, which is uxx plus uyy, and that's going to produce, and that's going to be equal to 0. So we want to find equations that are of that form, or functions of that form. So if we plug this in, we get q of y times p double prime of x plus p of x times q double prime of y is equal to 0. Right? That's just plugging in u to those to this PDE and setting it equal to 0. Now we want to find p and q, so what we do is separate. So to do that, we move equations over. We get 1 over p double prime is equal to 1 over q minus q double prime. And just like before, here is the x side, and here is the y side. And if you have some equation that only has x's in it, and another equation on the other side of the equal sign that is only a function of y, and they're equal to each other, it implies that they have to be equal to some constant. So I'm just going to put that unknown constant. So before that constant, we always had a negative sign on that. We'll let it have a positive sign, and again, this is a little trickier. So again, we don't know what that constant is, but we're going to solve for it. So what we're going to do is, of course, solve for the x side and the y side individually, and see if we can determine this unknown constant, and then with respect to the boundary conditions. So to do that, we solve for p and apply boundary conditions, and then we solve for q and also apply the boundary conditions. And then we should be able to multiply them together and to get back to our original solution, full solution to the problem. So let's go through this. So again, the equation was, we'll do number 1 first. It's going to be p double prime is equal to lambda p. All right. So for this, again, we don't know, lambda is unknown, and we don't even know what the sign is, but what we can do is go through a few cases. Case 1 is that lambda is 0. So that's case 1. And that's going to be p double prime is equal to 0. And because the boundary conditions for p, remember, we have f over the top of x, but then we have on either side there, for x equals 0 and x equals L, u is equal to 0 on that side and u is equal to 0 on that side, which means that p is equal to 0 on that side and p is equal to 0 on that side. Okay, so our boundary conditions are that x equals 0 is equal to 0 is equal to x equals L of p is equal to 0. Okay, so with p double prime is equal to 0 with these boundary conditions, the only solution is p of x is equal to the 0 function, which is trivial. So we don't even need to consider it, right? So now case 2. And that's going to be lambda is greater than 0. All right. So riddle me this. Do we remember the solution to this equation when lambda is positive? We know it when it's negative, right? It's going to be sines and cosines. But when it's positive, it leads to solutions of the form p of x is equal to c1 cosh square root of lambda x plus c2 sinh of square root of lambda x. Right, so these are the hyperbolic cosine and sines. So recall cosh of z. I'll just put the z variable in there to make it simple. Is going to be e to the z plus e to the negative z all over 2. And that sinh of z is equal to e to the z minus e to the negative z all over 2. And we know that cosh prime is equal to sinh, and sinh prime is equal to cosh. So the only difference between sine and cosine and hyperbolic sine and cosine is that the hyperbolic versions do not alternate sign as they cycle through their derivatives. You take two derivatives and you end up with the positive copy of the original, not the negative. So in this case, so now we remind ourselves about what sinh and cosh are. But then we have to solve that. We have to apply the boundary conditions, which is that p of 0 is equal to 0. And so immediately you see here that cosh, if I put a 0 in there, cosh is 1. So that would imply then that c1 is equal to 0. Okay? We can't have any cosh solutions. So then p of and then we also have to apply p. So p of x, the new candidate then is going to be sinh square root of lambda x. But then we're going to apply the other boundary condition, sinh square root of lambda L has to be equal to 0. Right? So sinh is only 0 only when z is equal to 0. There's no other zeros to the sinh function. And because of that, it would imply then that lambda would have to be 0. But we assume that lambda was greater than 0. Therefore, we can also assume that c2 is also 0. So case 2 is not under consideration in this particular problem with the boundary condition set on this side, like so. So that's F2. All right, so finally case 3. And this is the familiar case that we've seen before. Lambda is less than 0. And then we get solutions of the form Pn of x is equal to sine n pi over L x. Okay, and remember we don't consider the cosine ones because we know at this point that we have the condition that it's 0 on both boundaries. So we're only considering the sine ones. We already know what the constants are. So lambda is equal to n pi over L squared. Okay, apologies, negative n pi over L squared. So those are the eigenvalues. All right, so that represents a whole family of eigenfunctions that we will use next. So now what we need to do is go and do 2 now. So recall then that lambda is equal to negative n pi over L quantity squared. And now we have to solve the Q equation. Q double prime is equal to negative lambda Q. Right, and this is the equation in Y. All right, so if lambda is a negative number, that means negative lambda is going to be a positive number. So we just went through this. It would imply then that Q of Y is going to be equal to C1 cosh n pi over L of Y plus C2 sinh n pi over L Y. And now we do require then, remember our boundary conditions, so we have F2 on the top, but we require that U of x comma y equals 0 is 0, right? So it must be true then that the boundary condition we have to apply then is that Q of y equals 0 has to be 0. And again, cosh, when we evaluate it at 0, is equal to 1. So again, that would imply C1 is equal to 0. So we're going to get solutions. Q of y is equal to sinh, we'll call it Qn now, of n pi over L y. Sorry, that's sinh there, not sine. And so what about this boundary up there? So what happens when y is equal to h? Well, let's put that off till later. Together we can put the two solutions together, and so we have solution, a whole family of solutions. U of n x comma y is equal to p of n of x, q of n of y equal to sine n pi over L x times sinh n pi over L of y. So this is our family of solutions. And recall, this is from n is equal to 1 all the way to infinity. Each one of them works just fine. So we have this family of functions, and we now need to go assess this final boundary condition at y is equal to h. We want to know what's going on there. So what we're going to try to do then is say that u of x comma y is going to be some n equals 1, and I'm going to say to capital N, and n can be arbitrarily large, just we don't want to worry about it being infinite quite yet, of Cn times these solution families, the solution family, all right, and so what we want then, we want that when u of x and we set y is equal to h, we want that to be equal to f2 of x. So I'm going to rewrite this. I'm going to put the sinh in the front. Now we're evaluating y at h, and then times sine n pi over L x. Okay, so what we need then is, so now remember this is a constant now. So we need to go to a new sheet of paper. And I'm going to have to rewrite that, unfortunately. So f2 of x is equal to u at x, and y is equal to h. And that's equal to the sum n equals 1 to capital N, some very large constant, Cn sinh of n pi over L times h times sine n pi over L x. And just like we've done before, we do an orthogonal projection. We want to find the Cn, so we want to do this orthogonal projection. So what we do is with our functions then are our Pn of x is equal to sine n pi over L of x, n equals 1 all the way to infinity. And so what we're going to do then is, if this is our sum, then we go through and take an inner product of f with every p. And I'm going to now pick out a particular m value, right? Like that. And that will be Pm. And that's going to be, I'll put Pm there. And we have to write down this whole sum here. And then this right here is our Pm. That's our Pn of x, right? Pn of x. Okay, so we know that the inner product passes right through sums and any constant, and these things are constants. So we have f Pm, the inner product of f with a particular one of our orthogonal functions, our sine n pi over L x's, and that becomes the sum n equals 1 to capital N, Cn, sinh n pi over L times h times the inner product of Pm with Pn. All right, and recall then that this is equal to 0 if m is not equal to n. So that means the whole sum goes away except for one term, the Cm term. So that's m there. And we write that as follows. So Cm, our coefficients that we need to solve for, are going to be 1 over sinh m pi over L times h. And so this f was f2. I forgot to put that down there, right? All right, so this is for the specific case. Here's your f2. And it's 0 on all the other sides. So we're solving for that particular solution. So now let's go through and do a specific example. So recall that we had that specific example of f2 of x was equal to sine pi of x, and that was for L is equal to 1 and h is equal to 1. In this case then, C1 will be equal to 1 over sinh, because what this means then is with this we have f2 is actually equal to P1 of x sine pi of x, correct? So that means that'll be sinh of pi times just 1, right? Because you just evaluate PM, 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 and then that would also be PM. These would all be 1s. So and then, so that's it. So let's write down what the solution is. It looks like. So that means then, and then for all the other terms, Cn are going to be 0 for n not equal to 1. Okay, so that means our u of x comma y is going to be equal to our constant 1 over sinh of pi times sinh of pi y times sine of pi x. That's the full solution. So again, what does this look like? I can draw it. On this side, it's going to have sine pi of x, and it's going from 0 to 1. And here we have this is y is equal to 0, and that's y is equal to h. In this case, that's going to be 1. And here we have x is equal to 0. Here, all the way to x is equal to 1. And we know that it's on this side, it's going to be just sine pi x. All right, but what is it doing in the middle? So now we have a formula for it. So for every x value, there's this sort of shape here. But what does this do? So remember, sinh of pi y is going to look like e to the pi y minus e to the negative pi y all over 2. And when y becomes 1, so if y, if y is 0, if we plug that in, we get 0, right? So we actually know that it's going to be something like this. It's going to kind of come down exponentially, like that. And that's as desired, right? Because we wanted it to be 0 on all the other boundaries. So just to get an idea that I'm not lying to you, I actually plotted the graph of this. And there it is. So it's precisely what it is. So see, it's a nice hump, but it goes down. And this is an equilibrium temperature distribution for the heat equation. If we prescribe a temperature on the boundaries here, that's going to be non-zero. So it's going to be 0 on all these 3 sides here, but on this 4th side, we have this hump of hot temperatures in the middle and then cold on the edges. And we see that heat penetrates into the middle of our metal plate in the following way. So it's still cold everywhere on this end, and it's very cold on the outer edges there. But in this interior, we see that there is higher temperatures, and that will be the steady state temperature. So what's happening is, of course, the heat in this region here is spreading out and moving and then fluxing out the boundaries on all the other 3 sides. So you can think of there's a net heat loss or flux of heat through the edges on this side, and then heat is coming in from this top side there. So that should help you get it squared away. So the only thing you need to worry about here is that if you then decide to apply boundary conditions to the other 3 sides, the formula we used here only works for one of the sides. Now you're going to have to do the separation of variables and find out what the specific form of the solution. Sometimes they have sinh of pi y, and sometimes they might have something a little different, and you just have to be careful as you go through and do the separation of variables. All right, thank you.